So the paper I'm going to present today is the secret revealer, generative model inversion attacks against deep neural networks. So this paper has been presented in June 2020 in the Conference on Computer Vision and Pattern Recognition, or CVPR. So this will be a paper on my topic of model inversion attacks. And so let's start. So before moving to the details of the paper, a brief background that has been presented in the paper. So the paper talks about the wide applications of deep neural networks, such as in computer vision, speech recognition, and healthcare. So these compelling applications of DNNs involve the processing of sensitive and proprietary datasets. And as a result, they have raised great concerns about the privacy of using such data. So, one particular problem that can happen while applying these machine learning models is that it may leak information unintentionally about the training data through their output, which is known as the black box attack, or through their parameters, which is called the white box attack. So, brief overview of model inversion attack. In model inversion attack, it aims to reconstruct the sensitive features of the training data, and it does this by through the output of the models by using the model's output. And algorithmically, this is model inversion attack is basically an optimization problem where we seek to find the sensitive feature value that achieves the maximum likelihood under the target model or the model which is under attack. So next slide. This slide, I'll talk about the current landscape and challenges of deep neural networks. So thus far, according to the paper, effective model inversion attacks have only been demonstrated on simple models like linear regression, logistic regression, and decision trees, and there has not yet been very effective attacks against more complex models like deep neural networks. So a particular challenge in performing model inversion attack against deep neural networks, or basically inverting deep neural networks, is that they pose an ill-posed and interactability problem uh, when looked at the in the case of optimization. So what do you mean by this? It means that for neural networks, like even simple neural networks with one hidden layer, the optimization problem is a non-convex problem, which means that there are many local minimas, and hence solving it through gradient descent means that the gradient descent gets easily stuck in these local minimas, and this leads to very poor attack performance. And another challenge is that in attack scenarios where the model is a deep neural network, the data is basically uh, very high dimensional and continuous data. So it is very difficult to optimize over this high dimensional uh, data uh, without some knowing some extra information. So moving on to the contributions of this particular paper. In this paper, the authors focus on image data and propose an effective attack method termed the generative model inversion attack, which can invert deep neural networks and synthesize private training data with high accuracy. It They propose to use generative models to learn an informative prior from public datasets, to regularize the ill-posed inversion problem. And moreover, they present a theoretical result uh, that basically provides a connection between the model's predictive power and their susceptibility to general model inversion attacks. They conduct various experiments to showcase the performance of their attacks. And finally, they also show that differential privacy, which is considered a gold standard uh, when protecting against such attacks, is unable to protect against their proposed attack using generative model inversion. So in this slide, I'm going to explain their proposed GMI attack. So this figure illustrates the GMI attack method, which consists of a generative adversarial network, or GAN, with a generator. Two, there's actually two types of discriminators that's in the paper, not shown in this diagram, and a target network. So let's start with the generator. So the generator takes auxiliary knowledge as input. So this auxiliary knowledge is basically some added information that this paper uh, proposed to use, and this could be the blurring of images or images with uh, cent with a mask in the center. So the generator is crucial for creating images that resemble the private dataset of the target network. So after incorporating this auxiliary knowledge, it tries to produce some images, and basically the discriminator, there are two discriminators, as I mentioned. The global discriminator, which is responsible for the overall coherence of the reconstructed images, and a local discriminator, which focuses on the randomly selected patches, as, such as these center masks, and it tries to basically uh, make this recover this part of the image more consistently. So these two discriminators, they provide two outputs, and both of these outputs are actually uh, used in the generator. So the recovered images are the outputs from the generator, which have been basically refined through feedback from both the discriminators and the target network. The goal of these images is to closely resemble the original images in the private dataset. And then the target network is basically the network that is being attacked, which has been trained to perform a specific task like image recognition. So the reconstructed images are fed into this network to calculate the identity loss, which measures how well the generated images match the specific identities or features of the private dataset. Also, there's something called the prior loss, which comes from the discriminator. And both these laws together, they are used to guide the optimization process and improve the overall quality and accuracy of the generated images by the generator. So moving on, uh, this paper mentions a particular connection to image in painting. So what is image in painting? In image in painting, the goal is to fill in a missing or damaged parts of an image. So we can see how this is related to what I just explained before. So they mentioned that their generative model inversion attack borrows some strategies from image in painting to help increase the accuracy of their reconstructed images. Moving on, they this paper then provides a connection between the model predictive power and model inversion attacks. So the ability of a machine learning model to make accurate predictions is known as their predictive power. Uh, Another definition is that it is the difference in accuracy using all the features versus the non-sensitive features. So to understand a model's predictive power, especially the predictive power of the sensitive features, the authors measure how the model's performance changes when these sensitive features are excluded. So XS represent the sensitive features and XNS represents the non-sensitive features. And they basically experiment with uh, how, by removing the non-sensitive features, they experiment how the sensitive features is affecting the model's predictive accuracy or predictive power. So a critical finding is that with higher predictive power, the model inversion attacks success rate also increases, meaning that those models that rely heavily on the sensitive features for accurate predictions are more vulnerable to model inversion attacks. This is because these models establish strong correlations between the features and the labels, and this is exactly what the attackers exploit when trying to reconstruct the sensitive information. So, in conclusion, while predictive power is crucial for model machine learning models, uh, this paper highlights that there is a need to balance it carefully with taking privacy considerations into account. Now I'm going to explain the experimental setup of their approach. So they used three datasets for their experiment: the MNIST dataset, chest X-ray dataset, and celebrity A dataset, which they resized to 64 by 64. So to maintain a controlled environment, each dataset was split into two distinct parts. One was the private dataset, uh, and which was used for training the target networks, and the other was the public dataset, for which is used for providing initial knowledge to the generator. So this setup was crucial to so that their generative model inversion attack was fair and realistic. And the models they used, they use various models of various complexity. So for the MNIST dataset, they used a model with three convolutional layers and two pooling layers. They utilized ResNet 18 for the X-accelerated dataset, and they utilize these three VGG, ResNet, and phase.evolve in case of the celebrity A dataset. So the paper mentions usage of four evaluation metrics to evaluate their model inversion attacks. Uh, so there are peak signal to noise ratio, which measures the similarity between the pixels, and basically a higher PSNR indicates better image quality. Then they use attack accuracy. So this metric uses an evaluation classifier, which is different from the target model. And basically, this classifier is used to predict the identity of the reconstructed images from the generator. So if this classifier achieves high accuracy, it basically suggests that the reconstructed images resemble the original images very closely. Feature distance is another metric, and this basically uh, assesses the semantic similarity by measuring uh, the distance in their feature space. And finally, K nearest neighbor distance or KNN distance, which evaluates the proximity to the actual data points. So together, these metrics help to assess the model inversion attack performance, uh, which are like beyond, instead of just uh, evaluating based on how the images look. These metrics provide quantitative uh, metrics to evaluate the accuracy. So for results, they carried out their evaluation across three datasets, as mentioned before. They compared their generative model inversion attack with existing model inversion attack and pure image imprinting or PII. And they do it for three types of settings. One where there is no auxiliary knowledge or added knowledge. One where they have access to blurred images. And the third is where they have access to images with blocked identity features. So moving on, these are some of the results by their approach. So this table shows where the attacker has no auxiliary knowledge and how the GMI, uh, how their GMI, PI, and EMI, how these specific models are uh, having, the metrics they're having, concerning each of the four metrics. So this table basically shows that the GMI is showing superior recovery and identification capabilities, and they notably outperform AMI and PI across all models. So, for example, uh, here we can see that the GMI is having low value for KNN and feature distribution, while having high values for attack accuracy and top 5 attack accuracy. So moving on to table 2. This table shows whenever there is auxiliary knowledge available, such as blurred images or images with their center being masked off, uh, the GMI's ability to recover uh, private information is shown in this table. So it also shows the each of the cases like blurring, center mask, and face mask. I'll show the images after this slide. So it shows three of the models' performances. And we basically, the takeaway from this table is that the auxiliary knowledge significantly enhances GMI's performance, and the blurred and blocked images basically help test real world attack scenarios. So this image is uh, more understanding. So this figure shows a qualitative comparison of the proposed GMI attack with the existing model inversion attack. So, so it showcases basically the four cases. So one is without auxiliary knowledge. So without auxiliary knowledge, this is the target how for the actual network, and these are the reconstructed images from EMI, PI, and GMI. And we can see that the GMI is performing better or resembling the target images better rather than the other two models. Then when auxiliary knowledge such as blurring is available, so this is the target images, and these are the blurred versions of the images that were fed to the generator. and we can see how EMI, Pi, and GMI is performing. Again, we see that their approach is yielding the best results. Similarly, for center mass and for face TMAS, TMAS basically means that the eyes, the nose, and the mouth are the uh, important indicators of a person's face. They have been removed, and how still with just this information, the GMI is being able to reconstruct the image, which is very close to the target images, and the other two models are not performing as well. So the paper provides some more results. So table 3 showcases the GMI method's efficacy in recovering specific attributes from private images and compares it with EMI and Pi. So attributes like hair, color, hair color, eyewear, gender, etc., are evaluated across different scenarios, including no auxiliary knowledge, center mask, face mask, and blurring. So this table also shows that GMI is having better performance or better accuracy with the higher numbers than the other two models. This table 4 evaluates the influence of public datasets on GMI attacks success rate, particularly how the size and preprocessing of public dataset affect its attack accuracy. So here ratios like 1:1, 1:4, etc. These refer to the size ratio of the public to private dataset used in this study. So for example, 1:1 means that the public and private datasets are of equal size, whereas 1:4 means that the public dataset is 1/4 of the size of the private dataset. So this table basically shows that the GIMI attack uh, is still maintains effectiveness even as the size of the public dataset decreases, which is you can see by from these values, and when the public dataset undergoes pre-processing to better align with the private dataset. So without pre-processing, it is achieving this accuracy, and after pre-processing, it is better aligning with the private datasets distribution. So this is uh, another figure. So this figure demonstrates the GMI attacks performance against models with various predictive powers, and these are basically altered through uh, training size, dropout, and batch normalization. So part A shows part A shows how uh, the test accuracy and attack accuracy. Uh, it shows a linear relationship for all the models, and basically part B shows that like part A is for the training size, and part B is for when considering dropout and without dropout. So by considering dropout, the accuracy of all the models increases with compared to without using dropout. And part figure C shows using batch normalization and without using batch normalization. Finally, figure 3D compares the effectiveness of GMI attack on models with different privacy protection, known as differential privacy. So this figure shows that the GMI attack can still uncover private information even when models have strong privacy settings. And they find out that the privacy making uh, Making the privacy settings stricter doesn't always stop their attack from working. So, and even in some cases, the attack becomes more effective as the privacy differential privacy setting is increased. So this suggests that the way that we currently protect privacy in models uh, might not fully prevent someone from figuring out the sensitive details of those models. So finally, figure table 5. This shows the comparison of GMI against EMI on two datasets, MNIST and chest X-ray. So for both the datasets, GMI again significantly outperforms EMI in terms of uh, KNN neighbor, KNN distance, feature distance, and attack accuracy. So in conclusion, to summarize, the authors in this paper introduced a cutting-edge generative method for model inversion attacks, uh, and you, some of the things they incorporated is the uh, usage of generic knowledge to help improve their accuracy. Their approach, repa- they showed that the approach remained highly effective under various conditions such as unmatched identities, unlabeled datasets, small dataset sizes, and differing distributions of datasets. Moreover, they provided a theoretical analysis which linked the model's predictive power to its vulnerability to model inversion attacks. And finally, for future direction, they proposed to explore black box settings and develop effective defense mechanisms against model inversion attacks.